All right, so we have been talking about evaluating series when they're actually bounded. Now we want to think about evaluating an infinite series, which is crazy to think that we can do. So the sum S sub n of the first n terms of an infinite series is called a partial sum. The partial sums of an infinite geometric series may approach a limiting value. So this sort of gets into a topic that you'll talk about in calculus called limits, which for whatever reason, when I took calc, I really struggled with this concept. And I feel like it's because I didn't have enough practice with like series. But it's a really interesting idea. So example 1, you're not going to see anything in your homework like example 1, but it's an illustration of why this works the way it does. So we want to consider the infinite geometric series that's 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and so on. We're going to find and graph the partial sums S sub n for the first 5 terms, and then we're going to describe what happens to S sub n as n gets bigger. So let's just start with S of 1. That's just our first term, so just be 1/2. This is one place where decimals, I know normally we like fractions, but with graphing, obviously decimals they tend to be easier to graph. So I'm always down for decimals when we're graphing. Our second series would be the first 2 terms, which would be 1/2 plus 1/4, which I won't make you type that into your calculator, but it's 0.75. Our third would be the first 3 terms, so 1/2 plus 1/4 plus 1/8, which is going to be approximately 0.88. Our fourth is going to be 1/2 plus 1/4 plus 1/8 plus 1/16, which again is going to be approximately 0.94. Ooh, I already heard the question. We're wondering something. That's a good question. Let's see. So 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, we get about 0.97. So I already heard the question, does it ever equal 1? That's such a great question. Let's look on the graph and see why this is happening. So your x-axis is going to be our n. And I did skip a space here, but I'm counting by ones. So this goes up to 5, just so that we have more room to graph things. And then for your y-axis, which is really our S sub n, I'm counting by 0.1, but I'm only marking the 0.2s. So this is 0.2, 0.4, 0.6, 0.8, up to 1. So for my first term, my first n, this was at 0.5. For n equals 2, we were at 0.75. So that's halfway between 0.7 and 0.8. For n equals 3, I was at 0.88, so almost to 0.9. For n equals 4, I was at 0.94, so just under halfway between 0.9 and 1. And then for n equals 5, I was at 0.97.
Oh, is 1 the asymptote?
Yeah, you said the word right away. Yeah, 1 is an asymptote, or it appears to be an asymptote. So it looks like we're approaching this value, and it very much looks like one of our like exponential ones, right? That goes, it approaches the value, but it never crosses it. So your book has a more in-depth explanation for this if you ever want to look, but I sort of tried to summarize it down below. So the sums of infinite series. In example 1, oh, actually, let's finish example 1, sorry. So we can say, to answer this last question, describe what happens to S sub n as n increases. We can say that S sub n appears to approach 1 as n increases. Because again, we never connect these with like a line, because that's not what we're doing here. We're not saying that this value is in this sum. But if we did connect with it line, it would just kind of like bottom out at this what appears to be an asymptote. So again, your book has a more in-depth explanation, but let me just show you some of this. So in example 1, you can understand why S sub n approaches 1 as n increases by considering the rule for S sub n from this example. So if we were to consider this specific example, if we were to write a general rule, it'd be S sub n equals A1 times 1 minus R to the n over 1 minus R. This was our formula in the last section for a finite geometric series. Well, my first term was 1/2, and then it'd be 1 minus my rate is also 1/2 to the n over 1 minus 1/2. You would have gotten that rate by dividing this second term, 1/4, by 1/2, and you would have gotten 1/2. If you do some fancy algebra here, you can distribute it and simplify. This is actually equal to 1 minus 1/2 to the n. Now, let's think about 1/2 to the n. As my n gets bigger, what happens to this number?
It's smaller.
It gets smaller. Because it's 1/2, it would be 1 over, say, 2 to the second, and then 1 over 2 to the third, and then 1 over 2 to the fourth. So since that bottom number is getting bigger and bigger, when you do the division, the number gets smaller and smaller. So this gets closer to, it'd be like 1 minus 0.5, and then 1 minus 0.2, and then 1 minus 0.1, and then 1 minus 0.01. So it gets closer and closer to just 1. Because that 1/2 to the n approaches 0. So we can say as n increases, 1/2 to the n approaches to 0. So our series approaches 1. Now your book, again, this is where I shortened it. Your book has an explanation of how that jumps down to this formula here. Recognize this formula? I accidentally gave it to you in the last section. We crossed it off. It's back. Here it is. So this is the formula for the sum of an infinite geometric series. So the sum of an infinite geometric series with first term A1 and common ratio R is given by this rule S equals A1 over 1 minus R. Notice it's no Sn because we don't actually need to talk about the number of terms now. However, there is a caveat here. It's pretty big. Provided that R, the absolute value of R, is less than 1. Why does that need to be true? Why does R need to be less than 1? Again, look at this example here.
Because you have a negative.
It's not necessarily about the negative. What happened if this 1/2 was not 1/2? What if it was bigger than 1?
Numbers keep on getting bigger.
Right. This worked because what was getting bigger was the bottom of the fraction, right? That's why it worked. So if this number was just 2 to the n, it'd be getting larger. I mean, yeah, it'd be getting more negative because it'd be 1 minus, say, 4, and then 1 minus 16, and so on. But you can't, if we were adding up all those terms, we would get to infinity. We wouldn't get to a specific number. So this is really important that your absolute value of R is less than 1. Otherwise, it's not going to shrink. So let's look at, I'm only going to do 2 of these examples, actually, just so you have more time to work on your assignment, which, again, is only 5 questions. So this is what the majority, well, this is what your assignment will look like. I'm either going to give you the series in summation notation, or I'm going to list the terms. So let's look at what to do with both of these. So example 2a here, we want to find the sum of the infinite geometric series. So this is a little more straightforward because I'm looking for, again, this formula S equals my A1 over 1 minus R. And hopefully you noticed on a couple homeworks ago that as long as your index started with 1, we didn't have to shift it, that your A1 was right here and that your R was right here. Hopefully you noticed that. So with that, then we can just fill in this formula. Our A1 would be 5. And again, that's because this would be 1 minus 1 is 0. So then 0.8 to the 0 just goes away, and your first term would be 5. Over 1 minus 0.8. Before I plug this in, is our rate less than 1?
Yeah.
We're good. So if you type this into your calculator, you would get that this actually sums up to 25. Isn't that insane?
Yeah.
So if you were to graph this again, you'd have something similar happen where you'd have what looks like an asymptote at 25, and your points just get closer and closer to that when you sum them up.
So whatever the sum equals is the asymptote.
Oh, okay. Yeah.
Yes. I mean, I don't know that we could call it an asymptote. I don't know that that's actually what it's
Kind of
called.
what it, okay.
But yes. All right, one more example.
One more example.
One more example. Let's look at part C. So this is an example where I'm not giving you the series notation, that summation. So again, our formula that we need is S equals A1 over 1 minus R. So let's just remind ourselves where everything is. A1 is going to be that first term. So it's just 1 here. My rate is a little trickier. Remember the rate, you can take one of these and divide it by the one before it. So I always do A2 divided by A1. So this would be -3 over 1. So my rate is -3. Am I good to plug this into the formula?
Yep.
You sure?
Yep.
What's the issue?
Ours is.
Yeah, the absolute value of R is not less than 1.
So it has no sum.
Right, so we can say, and you don't have to put this in Go Formative, but for our notes, because the absolute value of R is greater than or equal to 1, it is also, if it's equal to 1, you can't do this. The sum does not exist.
So do we just like know, like, what, how do we put that?
Yes, so in Go Formative, no sum. Any questions about this at all?
Nope. Is that it?
All right, that's it for today.